right, we're up to problem 15. We're given the pressure and the enthalpy. So I'm going to go to the saturated chart and look for this pressure, 42,000, holy smokes. Let's see here. Yeah, of course, the pressure is higher than the highest pressure listed in the saturation table. So what that means is that we are above the saturation dome. And if you look at these saturated liquid line and saturated vapor line, they approach each other as the pressure and temperature rise. And you can see that in the chart, right? The saturated liquid, saturated vapor specific volume actually come to the same value when we reach this critical pressure, the top of the dome. Same with the internal energy and the enthalpy and the entropy, same values, meaning that the last line on this saturated water chart is that critical point right there. So at 42,000 megapascals, we are way above the dome. We are clearly superheated. So I doubt that I have a 42,000 megapascals. What do I have? It looks like I have a 40 megapascal and a 50 megapascal. So I'm going to have to do some interpolating. So this is my interpolation. I've already got it set up here. What I wish I had is a 42 megapascal box, but I don't. So I'm going to have to construct it by linear interpolation. So I'm going to write the 40 and the 50. That's these two columns. And I can see that my enthalpy given was 3,200. So I go down and kind of find 3,200. It looks like it's bouncing around between 550 degrees Celsius and 600 degrees Celsius. So I copy those lines down. I create a 550 degree line and a 600 degree line. And I copy the enthalpies from those two sections of the chart. And what I'd like is to construct this line. Let's keep our eye on the ball here. What I'm after is the temperature right there. So in order to get that, what I need to do is to be able to interpolate using 3,200. But I need this value, and I need this value, so then I can interpolate that way. So first thing I'm going to do is interpolate between the pressures and the enthalpy, and the pressures and the enthalpy. That's what this is here. So I'm going to interpolate 40 minus 42, 33. That's this line to here. So that's kind of this minus this times that. And then I'm going to do this minus this times that. So you can see that's what I set up. All divided by the distance, 40 minus 50 megapascals. Again, don't worry about the sign. Just keep them in there. Keep them in your calculator. It'll all work out in the end. And you can see the units all cancel. And I'm going to be left with this kilojoules per kilogram. So the first value I get is this 3124.53. If I interpolate again between the next set of values, you can see what I'm going to get. Here's the interpolation for 40 minus 42 times this 32, and then 42.315 times minus 50 times this 3550. That's what I've set up here. Divided by the 40 minus 50, and I get 3327. So I'll write that there, 3327.7593. And it's a good idea to make sure this kind of makes sense. This 42 is almost smack dab in the middle of 40 and 50. Not really. It's actually way closer to 40. But so I expect this makes sense, right? This number here, 3124, is kind of closer to 3154 than it is to 3100. Similarly here, this value is closer to our 40 megapascals than our 50 megapascals. That makes sense. So the last thing to do is interpolate between these values in order to get the temperature. So that's what I've got here. I've got the temperature is 3124.53 minus 3200 times 600. That's this difference, plus this 32 minus 3327.75 times 550. It's this one, and then I end up getting 568.56. So that goes here. Our temperature is 568.56. I know that it's a superheated vapor, and it doesn't have a quality as a result.